In this video, we're going to talk about a new concept called momentum. And momentum is a way of describing how objects move or behave when they experience messy forces. So what do I mean by messy forces? Well, so far you've learned about Newton's second law, net force equals mass times acceleration. The problem with that equation is it implies there is a single net force that's always the same, a constant force. But that's not really accurate for things that are exploding, for things that are crumpling, like this can. Those forces are changing. So momentum lets us relate motion to forces that are changing. And that's what makes it a useful concept.
So let's look at a motion that doesn't have a constant force, and therefore we can't use the constant acceleration model that we've built up so far.
Have you ever thought about how a tennis ball bounces? What about that collision? What kind of forces are acting there? Well, you probably didn't notice any change in the tennis ball as it went through that bounce. But let's look at that same collision between a tennis ball and a textbook at about 1,000 frames per second. And then maybe we'll get some insight as to what's going on.
It's not something we can observe directly, but when a tennis ball hits, and we can see this at 1,000 frames per second, it deforms slightly. Let's go to the exact time of hit so we can see a little better. So it's only a few frames out of 1,000 frames per second, but we can see that the tennis ball definitely is smashed in. And we should think about what kind of forces it experiences as it goes from being round to being smooshed like this. So we expect that when the tennis ball first hits, there's not much force, but the more we squeeze it, the larger the force required in order to do that. And that force is going to increase and increase and increase as it starts to smash in until it reaches a peak. There's no reason to assume this is linear. In fact, it's not. I think as it slows down, we expect the force to change less and less. The peak force is when it's actually stopped at rest for a second on the textbook. Then what happens? It changes direction. And it starts to unsmoosh, so the force is going to go away. So we get this kind of bell-shaped force curve, and we don't really have a way to deal with that. All the force versus time stuff we've seen so far has been dealing with constant forces. With constant forces, we could use all our constant acceleration equations to talk about motion. But none of this is valid for this kind of model. So we have to come up with a new plan. So here's the new plan. I've drawn a bunch of non-constant forces, and we can see that they have a lot of different shapes. But if we're trying to figure out how an object's motion changes, presumably having more force and applying that force for a longer time are both important. So that led people to think, how can we combine the effects of both force and time for variable forces? And by looking at the graphs, it suddenly becomes clear. Check out the areas under these graphs. If the area is big, like in these cases, that means that we've got relatively large amounts of time and relatively large amounts of force, even if that force is changing. We expect this situation to be an object whose motion changes kind of dramatically. This one here, there's a lot of time but not much force. We don't expect this one to be as dramatic a change. So this area under the curve is actually a really good visual way of telling just how much are force and time going to combine to change an object's motion. So the area under the curve on a force versus time graph is so useful in determining how an object's motion changes, we give it its own name and symbol. We call it the impulse, and it gets the letter J as its symbol. So all we have to do to get the impulse is find the area under a curve. That can be complicated for strange-shaped functions like the one we saw with the tennis ball hitting the textbook. In fact, that's why a whole field of math called integral calculus was invented, to get the area under various mathematical functions. Turns out that's pretty important in science and engineering. We can get around that complex math, though, by just pretending that instead of having a variable force, we had a constant force that acted the entire time the tennis ball was in contact with the textbook. Now, for this imaginary constant force to have the same impulse as the real force, it has to be an average force. In other words, it's not as big as the peak force. It's not as small as the minimum force. But imagine this red curve and the orange curve. If we drew areas, if we found the area they enclosed, imagine they would be the same. Then the both forces will have the same effect on the object's motion. This means it's pretty easy for us to calculate impulse. We just need to know the average force that happened during that collision and multiply it by time. Impulse equals average force times time. So I keep saying that impulse gives us clues about how an object's motion changes, but now I gotta be specific. What does an impulse cause? Well, it can't just be an acceleration, because we've seen the net force causes acceleration. An impulse is more than that. It has to do with both force and time. So impulse changes something else about an object's motion, a new concept that we now have to define, a concept called momentum. So in order to keep track of these variable forces, it helps to pay attention to another quantity called momentum. And objects can have momentum, and what's nice about the concept is that momentum means exactly what you think it does. If you're watching Monday Night Football and the announcer says something like, "Ho ho, the Jets this year have a lot of momentum," most people know that means that they're hard to stop. And that's exactly what the word means in physics. Momentum is a measure of how hard something is to stop. So, what are the two things that could contribute to something having momentum? Well, those are not too hard to guess either. It's very hard to stop a freight train, even if a freight train is moving very slow. And that's because it has a lot of mass. So, mass probably has something to do with momentum. It's also very hard to stop a bullet. And a bullet doesn't have a lot of mass, maybe only a couple grams. But what makes it hard to stop is that it moves so fast. It has a big velocity, hundreds of meters per second. And those are the two things that make something hard to stop. So momentum has to include both of them. Luckily for us, it doesn't get any harder than that. The equation for momentum is just mass times velocity. Momentum gets abbreviated P sometimes for persistence, which is another word for it. Someone who's persistent is hard to stop. So if we keep track of the momentum different objects have, that's going to help us understand the forces that are acting on them. So I've got a can here, and if I give the can some momentum, it's not enough to just tap it. It keeps going. If I want to actually stop it, I have to apply that tap for some time. And that's the important thing to understand about momentum. You can't change it just by applying a force. You have to sustain that force for a certain amount of time. So this final line looks a little intimidating, but here's that force and time we just talked about. I needed both a force, I needed to apply that force for a time in order to stop the can. And if you multiply the force and the time together, you get this concept called impulse. So an impulse is what changes an object's momentum. This part over here just says change in momentum. The object's final momentum minus original. But don't get hung up on that. If you want to change how hard it is to stop an object, you have to apply a force for a certain amount of time. Alright, so what can we use this idea of impulse and momentum for? Well, it can give you a choice. Let's say you have to change an object's momentum. Let's say it's an object that's moving a certain speed and it has to stop. You have a choice. You could be gentle, and that would mean applying a smaller force, but it's going to take you a long time. Let's see what that might look like.
When I get on this tricycle and drive up onto the grass puts a small force on me and stops me gently. And it takes a long time to stop me. You also could be not gentle. You could apply a much bigger force and have it done in a shorter time. Let's take a look at that. Watch what happens when I slam into the back of a car, which can apply a much bigger force. What do you think will happen to the time it takes to stop me? All right, here I go. So thinking about impulse as the area under the curve on a force time graph, we can see what's going on with these two situations. When I was stopped gently by the grass, that was a small force that lasted a long time. When I hit the back of the car, that was a big force that was over quickly. But they had the same area under the curve, so they changed momentum in the same way. I had a certain speed, and then I went to no speed. So this has pretty serious safety implications. This is a choice you can make. Gentle means you're going to have somebody in motion for longer. Harsh means someone's going to be in motion for a very short time. This is why you have airbags in cars. An airbag, as the person hits it, it starts to deflate, and that keeps them moving for a long time. That's going to put less force on them. Without the airbag, you hit the steering column and it's over quickly, but that means your body has a big force and you get hurt. So impulse has pretty serious safety implications. I wanted to finish this lesson on momentum and impulse with a problem that shows how to use both ideas. So we have a baseball player who's hitting a fastball, and it's got an incoming velocity, an original velocity. They hit it back with a final velocity, and we know the mass of a baseball, and we're asking about what is the average force. We also now know the contact time, 1,000th of a second. So what you basically do is you say the impulse equals the change in momentum. The impulse is average force times time. That equals mv final minus mv original. Notice I've plugged in a negative sign for one of my velocities because it is switching its direction from going towards the batter and then going away from the batter. So I end up with a change in momentum of 12.31, and then by dividing by the time, I get an average force, which is 12,310 newtons. If you calculate that out, and you wouldn't have to do this, that's about 2,700 pounds, which is a huge, huge number. And actually, the real force on a baseball would be even more than this because we just calculated what the average force was. So the real force would be a lot more. That may seem crazy, but the bat only is in contact with the ball for a very, very short time. And it's worth looking up some high-speed photos of what it looks like when a bat hits a ball. And you'll see that the ball deforms quite a bit. It really does have a large force on it. So hopefully this equation is less threatening now, and we're going to practice using it a whole bunch.